All right. Thank you all so much for being here and for having me. Quick plug for some friends of mine in the community. If you have thoughts on math preparedness for your students, take a second to grab a link to the survey, and I'll use that time to vamp a little. I've got a couple notes. I'll try to keep this whole talk to about 45 minutes so we have time for discussion after. And I would maybe recommend that you jot down notes because this one's a little ragged and a little stuffed. There's a lot of ideas in here that I don't have time to discuss in full depth, but I'd be happy to circle back later. The last time that SIGCSE was in St. Louis was 21 years ago. And the last time I was in St. Louis was attending that SIGCSE as a doctoral consortium student. So shout out DC. Uh, SIGCSE was my preferred venue as a grad student, and I vividly remember a few things from that era. The last time I was here, I wandered these halls filled with the common grad student aspiration. I hope to make it onto those stages someday. I didn't dream to dare big enough to imagine myself on the big stage giving a keynote like this, but I certainly hoped that I could be part of the bigger conversation and help move the needle for the field that I still care so much about. The last time SIGCSE was here was also the first year that ICER was held, and I published there as well. By that point, my wife had begun studying math and physics education research, and those disciplines, I always heard, had so many decades of head start on us in terms of treating STEM pedagogy as a problem that was suitable to experimental rigor. Depending on your perspective, the formulation of ICER might have been get those theory people their own space, or just we need a separate track focused on rigor and theory building experience report. How do we as a community learn from other STEM disciplines and rigorously prove that one teaching technique works better than another? That line of investigation has been running in CS Ed for several decades now, but we do have a harder job, I think, than physics or math because once you get past a few basic theory axioms of computability, a whole lot less of our field is governed by fundamental laws of reality. You can be wrong and nothing's going to push back. We can and do, as a field, have much more fundamental disagreements on what is relevant, what is necessary, and what is even true. The last time I was here, I was all about looking forward. And with a little bit of age, a couple of gray hairs, I think it's fascinating and important to look back on those moments in time. Largely due to the two-body problem, I went down the industry track instead of continuing my involvement in academia and spaces like this. And initially, I looked on that as a failing. I took the road more traveled and gave in to the lure of the industry. But eventually, I did make my way to Google, where I spent 13 years in a very odd role as eventually one of the prime stewards of Google's C++ monorepo. I talked to thousands of engineers, maybe tens of thousands, and I learned a lot of lessons at the hard way at scale about software engineering, C++, efficiency, and the use of soft power for managing a large community. I eventually evolved my role into one that had a deep focus on teaching and education internally for all of those engineers. It wasn't academia, but it was still driven by the same ideals that I always have loved. Finding those deeper truths, disseminating important ideas, helping people around me grow, and making everything just run smoother because we understand the nature of the problem. I just had to do this with corporate performance reviews instead of a publish or perish initiative. It was a very roundabout way to get me back into a search for truth and a focus on education, but it did enable me to get back here, so I certainly can't complain. While cherishing those memories of the last time that we were in St. Louis, I want to also specifically dedicate and direct this talk to the grad students and the junior faculty out there, because I think you're going to be really important in what's to come. So hang on to your seats and you'll see what I mean. Those of you that can find a path and the will to act on this call to action may well be standing here leading the rest of us in a few years. The last time that we were in St. Louis, I could never have imagined the path that would bring me here or that I'd be standing on this stage. Much less would I have guessed at the topic of the day or the question that I have to ask next. While I keep saying the last time and meaning 2005, What if this is the last and final time that we need to meet and talk about computer science education? That's inflammatory, and it is a little bit hyperbolic, but we really do need to consider what we are up against. In my view, the theory and practice of computing have diverged hugely, and AI threatens to obviate a lot of outmoded tasks and ideas. The industry and our field are in a period of incredible chaos and uncertainty. While we're used to dealing with accelerating enrollments and the crisis of oversubscription, suddenly we're seeing enrollment down in many places, and tech hiring has stagnated. According to the most recent stats from the New York Federal Reserve, CS grads from 2024 have a slightly worse unemployment rate than grads in the performing arts. And of course, everyone is trying to predict what lasting impact AI is going to have on all of us. I hope that you're tired of hearing about AI. I certainly am. I have been wishing for years that we could just get over the hype, that the bubble would burst already, that the more skeptical and level-headed voices would take control of the conversation, because this is just so much. As recently as last summer, I was giving talks on how bad the models are and how much I felt like I was being gaslit. For years, everyone has been saying, oh my God, look how much better AI is. And I keep going back to a handful of my litmus tests and just saying, no. A couple of those tests fit on slides nicely, and I'll use that to sort of illustrate my point. While I was at Google, I helped out with the relentless interviewing process, usually by handling the phone screen questions. And the nature of a phone screen is very simple. It's if a candidate is actually fluent programmer, let's talk to them more. And so I asked some pretty easy questions to get a sense of whether they can actually, have code come out of their fingers. And if they do well on that, we might have time to ask some deeper and more interesting questions. But in practice, it's a basic skills check. Can you program? To that end, this is the question that I gave to perhaps 100 candidates over my time at Google. Given a well-formed non-negative base 10 encoded integer as a string, add 1 to it and return it in the same format. The core complexity here is carry the 1. I was generally interviewing in languages where there was a mutable string class, and in other languages like Python, I would tweak the specification so that the input was at least potentially mutable. If you can modify something in place, iterate in reverse, and do some basic logic, you should be fine here. This is, after all, the earliest thing that we learn as, we're age 5 or 6. Like, you could call that an algorithm. As of last summer, every model that I asked this question produced something that technically worked, but exhibited at least a few of the smells that would be present in a poor quality human implementation that I saw so many of. You'd have an explicit carry instead of relying on the loop structure to handle whether you are still carrying a 1. We would use div and mod operations when it's entirely unnecessary. The range of a digit plus 1 is 1 to 10. Increment and logic work just fine. They match how we describe the problem when we talk about it out loud, and they're dramatically faster. Why would we be doing complicated arithmetic? Mixing up the integer and character domain was very common, but most bothersome to me was the ways that models tended to pessimize. Done well, you can match the specification for this project and do the work in place, meaning that a good implementation is best case and average case constant time. A poor solution, whether from a human or an AI, tends to accidentally make that linear time best case. While algorithmic complexity is not all that we make it out to be, dropping from order 1 to order n shouldn't be done without some thought and care. As of last month, ChatGPT is still producing low quality but technically correct results. And historically, this is roughly what I get from most of the models. It's doing the carry thing, it's doing the div and mod thing, it's forcing the whole thing to be order n. But it does work. Interestingly, if an interview candidate produced this, I would be spending 5 to 10 minutes nudging them to simplify, whereas, I can get this in 20 seconds. And something like this is actually what I'm hoping for, right? We do the work in place, start at the end. If it's not a 9, you increment that digit by 1 and we're done. Otherwise, it's still a 0, or it's still a 9, so make it a 0. If we make it to the beginning, we have changed a string of all 9s to a string of all 0s. In an ideal world, prepend a 1. Actually, no, in an ideal world, set the 0th element to a 1, and postpend a 0. But by that point, we're already doing order and work, and so I'll grit my teeth and deal with it. But Claude and Gemini generate roughly this, which is pretty close to that optimal solution, only missing the bit of cleverness in the length extension case. In practice, if a new grad produced code that relied on 1 or 2 of these smells, the odds of them solving the problem accurately within 15 to 20 minutes were pretty low. And one of the weirdest things for me about AI has been that it constantly generates low quality stuff with all of those code smells, but it does manage to juggle the details well enough to get something that compiles and passes tests. Messy, low quality code used to be highly correlated with doesn't build, doesn't work, couldn't possibly be shipped. But machines are now pretty good at handling the raw functionality, even when they're shipping out kind of messy results. For a more visceral example, as of last summer, you could always get a pretty good laugh by pulling up your AI of choice and asking it to generate a single page for a children's alphabet handout. We get letters skipped, we get letters and words paired wrong, words and images paired wrong. It does not stand up to 10 seconds of scrutiny. And you can, I have done it a couple times in a bar, spend 10 minutes studying this and not find all of the ways that AI has failed us. As of last month, I'm not laughing anymore. We skipped Y here, and the picture for X is not a xylophone. But generally speaking, the level of accuracy has gotten a ton better. And that's just the base models. That's not even including in the coding arena, advances in tooling and agent interaction and AI integration in our IDEs and tools to better manage context and enterprise tools for doing all of this at scale. For the skeptics out there, I do need to drive this point home. The tech industry reliance on these tools is not going away. Studies last year pretty consistently suggest a 5 to 15, maybe 20% net gain in software delivery efficiency. Google's CEO claims a solid 10% efficiency boost for an absolutely massive organization. And that might sound like not a lot, but it is a very large amount in the industry terms. Even a 5% change in productivity or efficiency is a huge deal. Consider just the basic economics. Estimates vary, but there are roughly 25 to 30 million software engineers in the world. If we ballpark that they earn 100 grand annually, that means the total cost of engineers right now is $2.5 to $3 trillion annually. So a 10% gain in engineering productivity is perhaps $250 billion globally. That is on par with the GDP of New Zealand. And that estimate is based on the gains from a year ago, ignoring all of the model and tooling improvements that are actually starting to scare me now. So if it was worth that many billions of dollars and the tech has advanced meaningfully in the last few months, no, business leaders are not going to walk away from this willingly. And that makes me sad. I would love for all of this to just disappear, but it's not going away. So even as a deep skeptic, I come to you today to drive home this point. None of this is going away. Workflows and problem-specific models, the coding models, the tools, AI-integrated IDEs, it's all continuing to advance at a terribly rapid pace to the point that even a moderate skeptic like me has pretty regular crises of faith. The other extreme of this, though, it's not all lost. There is the viewpoint that specification is the only important artifact and code is going the way of the dinosaur. This is the AI true believer viewpoint, saying that quality doesn't matter. Humans don't even have to look at the code. We can just specify all of the requirements and the contracts at every level and regenerate code as needed, or if and when the models improve. You get examples of this thinking with stories like the Anthropic C compiler generated in just 2 weeks, mostly hands-off by a swarm of agents. That is a pretty flashy headline until you dig into the details and you get things like doesn't have an assembler or linker, generates worse code than unoptimized GCC, the Rust code is nowhere near expert quality, etc. And the blog post details a lot of interactions that the researcher had to do and framing needed in order to get to even this level of quality. We spent a bunch of time getting all of the unit tests from all of the well-known public open source compilers like GCC in order to keep the agents on the rails. Even this stunt wouldn't have worked without prior expertise. And let's be honest, generating a C compiler, that is probably the single best specified, most understood big systems project in history, because we've been writing C compilers for a good long while, right? The mostly hands-off is hiding a lot, and the end result here is not honestly fit for any good purpose, right? AI can do the functional part, but the prompt is not enough. The prompt can perhaps get that functional correctness, but because the AI can write code in the same way that we have been training students. Meet the specification, pass your functional tests. Quality is too hard to define, specify, require, grade, prompt for. AI can program, but it takes a different set of skills to make that useful. And unfortunately, in many cases, I think that what we have been teaching students is exactly the skill that AI is good at: how to write technically functional code without a substantial focus on quality. As a field, we have spent decades focusing on teaching students programming and how to demonstrate and define functional correctness. So I guess we're done, because that's what the AI does, right? Congratulations, everyone. We did it. We automated ourselves out of a job. There is nothing more to do. It's an honor to be the last keynote presenter at the last conference. Whoever is the last one out, make sure to turn out the lights. Sorry about Sacramento. Again, no. But if we don't change what we are doing, that may well be what we face. Luckily for us, AI is not clever or innovative, and it's only so-so on precision, and it's only so-so on quality. I mean, for as impressive as it is to generate an image like this from a 26-word text prompt, we should still keep in mind that it got the number of letters in the English alphabet wrong. AI is not going away. Students are going to use it because employers are going to suggest, or actually mandate, that they use it. Interviews, the tech interview is switching to rely on it. The elite code interview is dying rapidly. It's going to be AI for sure, right? This is not the way that I wanted to win that one, but I'll take it. The trick for us has to be to realize that the skill has shifted. We used to believe, whether rightly or not, that generating code was the bottleneck, was the hard part, was the thing that separates a well-trained computer scientist or software engineer from your average person on the street. That is no longer true. But crucially, I don't know that we were doing a great job of teaching coding fluency before. I have been thinking about and scared by a quote from Harlan Mills that dates back to 1983. Harlan said, "Our present programming courses are patterned along those of a course in French dictionary. In such a course, we study the dictionary and we learn the meanings of French words are in English. At the completion of such a course in French dictionary, we invite our students to go forth and write French poetry. Of course, the result is that some people can write French poetry and some not, but the skills critical to writing poetry were not learned in the course that they just took in French dictionary." To my mind, Mills's critique is more relevant and urgent than ever before. I think that the point he was trying to make is that we focus a lot of our instruction on isolated concepts, on the definitions needed to get over the hurdle of being able to assemble something, but we rarely give attention to the greater whole, or the emerging quality of the resulting program, or the beauty of the underlying code. We spend a good chunk of time teaching about recursion or binary search trees or linked lists or regular expressions, but we rarely convey the wisdom of, please don't use these except in very specified specific circumstances. We say that this is a discipline that relies on craft and cleverness, and then we treat most assignments as a meat grinder exercise so that it can be fed into an autograder, which leaves our students with the impression that programming is just a matter of translating specification into code, pure functionality, and little consideration given to quality. We talk about how hash tables are implemented, perhaps, and we fixate on the theoretical worst-case performance, but we ignore the practical efficiencies. And we often fail to convey the understanding that an associative container, whatever its backing might be, a dictionary, a map, call it what you will, an associative container is one of the most powerful fundamental primitives for a programmer. You have to have that concept of when to reach for a map, more so than you need to have, how do I implement such a thing? I'm reminded of an example that a friend of mine had from an algorithms TA. The assignment was a classic ICPC, breadth first search, open the lock, right? You have 4 dials, 0 to 9. You can rotate them clockwise or counterclockwise. Some states are forbidden. Find a path from start to end. You've probably seen this problem. Suggestion from the TA was to allocate 10 to the fourth nodes separately with data members for all of the things that you could imagine, and then go through another pass of that to remove pointers to any node that was in the forbidden list, and then do breadth first search of the node pointers. And in theory, sure. In practice, nah, right? In theory, there is no difference between theory and practice, and in practice, there is. Anyone that has spent much time in ICPC practice or doing LeetCode competitions will have eventually iterated to a much simpler pattern and abstraction for breadth first search. But it's the practice and iteration that lets them refine that understanding of how to implement this problem. You define the representation of a state. Here I'm using a string of digits because I'm a C++ nerd and I know that modern string types have enough inline storage to ensure there's no heap allocation or pointer indirection. It's all fine. Define a function that takes a state, returns all of the valid one-step neighbors of that state. I'm keeping that simple here. You don't really need to care about the code. With appropriately chosen data structures here, even on a state space of only 10,000 nodes, which 10,000, I forgot how to count that low. A good solution here is twice as fast on average as the type of thing that was described by the TA. And I measured that and benchmarked it on literally every possible starting state with an equivalent number of forbidden states. So I come with data. As well as this is going to be easier to learn, reuse, use, maintain, all of the above, right? But you have to practice to get there. You have to play with it. To my mind, the reason that tech interviews have been focused on these sorts of algorithms problems and elite code interviewing for so long is because the industry recognized, maybe implicitly, that what we need are the students that have spent extra time practicing. Like Amy said, that have had the time to experience the joy of just like, I'm just doing a thing and someone supports this, right? It's not, I'm doing this for the grade. It isn't that industry wants any of the short-lived and messy code that comes from this type of work. And it isn't that those questions have any relevance to what students are going to do in the industry going forward. It's entirely that the students that have had that time to practice and play have a higher chance of understanding higher level code and abstractions. The oft missing process of practice and drill and iterative refinement enables us to find the more elegant places to generalize, to decompose, to understand the real nature of the problem. It's French poetry. It's programming fluency. It's not, do you know what a loop does? It's how do you spot an invariant? How do you decompose? What's your grain size for understanding? We now have tools that will automate away the code generation and fix all of the compiler errors. It is time to move past French dictionary and focus on poetry. And in my mind, that's the future value add for CS and software engineering education. And that's in line with the broad theme that I see around us everywhere in responding to AI. The AI disruption, more than anything else, makes long overdue changes become urgent all of a sudden. We see exactly this in the software engineering space. Industry-leading researchers that I quote all the time summarized AI this way in a paper last fall. The research reveals a critical truth. AI's primary role in software development is that of an amplifier. It magnifies the strengths of high-performing organizations and the dysfunctions of struggling ones. Greatest returns on AI investment come not from the tools themselves, but from a focus on the underlying systems, quality of the internal platform, clarity of your workflows, alignment of teams. Without this foundation, AI creates pockets of productivity that are lost to downstream chaos. I tend to be a little bit more colorful in my description. AI is the Wile E. Coyote rocket-powered roller skate gag. If you have already cleared the road and ensured that you are aiming in exactly the right direction, AI will accelerate your good results. But if you still have long overdue roadblocks and potholes and speed bumps, or you're not aiming in quite the right direction, you're going off the cliff real soon. For the industry, this means that we have to focus on cleaning up our workflows, platforms, tech debt, and do what it takes to make it easy for humans or agents to make changes. For a lot of companies, those investments have been important but not urgent and easy to defer and kick the can down the road until now, and everyone's panicking. They wish that AI will turn into a silver bullet that fixes all of their old mistakes. And that wishful thinking contributes mightily to the hype and confusion in the tech press. So please continue to be skeptical. In the computing education domain, the long overdue discussion ties back to French dictionary. Is it enough to give our students an introduction of everything, but no mastery of the basic concepts, to give them a taste of every topic in the upper division, but not to give them taste? Perhaps at root, my question for you is, what is the relationship between the standard curriculum, CS theory, and tech practice? What is it today, and what does it need to be as we go forward? When I was doing the CS 2023 work, I would ask regularly whether CS is the big tent under which other computing disciplines fall, or is it the theoretical focus of computing disciplines that underpins everything? That is CS like an engineering department with specializations for chemical, mechanical, electrical? Those would be our data science, software engineering, security, et cetera. Or is it the math department that provides a logical substrate of understanding that underpins all of those applied sciences? And to my mind, the way this room reacts to the AI crisis is going to answer that question definitively. If we look for more fancy ways to teach French dictionary and call AI tools cheating, in a few years, it will be very clear that boot camps and SE departments have all the students. My belief has been for a while that CS departments have been far too slow to adapt and too focused on theoretical understanding that was useful decades ago. And as a result, CS is substantially at risk of being the theory branch, ceding mainstream focus and degrees and student population and relevancy to more specialized branches of computing. But AI is giving our field one last chance. As we pivot to react to the greatest technological upheaval of a generation, we have to rethink things anyway. Perhaps we should take stock more generally and reestablish CS as the big tent. If we do this thoughtfully, I think maybe we can even show other disciplines outside of computing how to react to all of this in a more constructive fashion. The other side of the spectrum, there's a question on my mind has been, what is software engineering? And the answer to that has been clear for almost as long as we've had the term. Brian Randell said all the way back in '74, software engineering is the multi-person construction of multi-version programs. It's people and time that makes software engineering different than programming. It's difficult, if not impossible, to make lessons about people and time be entirely authentic in the constraints of an undergraduate class. So I'm certainly not asking for that particular focus and mastery. But the things that do make a technical solution more appropriate in a software engineering domain are well worth introducing and leaning on, and we do that. Testing, communication, maintainability, design, documentation, comments. Coincidentally, those are basically exactly the skills that are needed to most reliably use AI coding tools well and responsibly. The old problems are urgent. We should focus on the new emerging basic critical skill sets, and that naturally will broaden us away from base functionality and dictionary and open up room for us to teach about higher level structures, higher level thinking, design, quality, and taste. The skills that are needed for AI to work well are the things that are needed to be a good engineer. And the things that come from practice and experience are the difference between splatting out some code, whether as a novice or with an AI, versus understanding the quality of that code. So I'd like to move towards a few specifics and look at what I think is silly or broken in the standard CS curriculum and just throw some ideas out about how eventually we pivot in order to stay relevant and useful. So here's some random topics that I often have to retrain junior engineers out of. We'll talk data structures. How much time do we spend in first year CS talking about binary search trees? Does anyone here teach data structures and not spend at least a week of lecture time going over this? I don't see any hands, right? It's ubiquitous. Oh, there's one over there. It's ubiquitous. So we should understand, if everyone's doing this, why are we doing this? Of course, we look at big O tables like these, and we compare trees with other associative containers like hashes. And when stacked up like this, it's obvious that hashing is subpar compared to a high-quality, balanced binary search tree. Woo! So why am I spending keynote minutes talking about something so obvious and basic? In the mid-90s, Wolf and McKee published Hitting the Memory Wall in SIGArch. It's on a typewriter. This paper points out what they describe as obvious and what they portray as a nightmare scenario. Application performance may at some point be dominated by memory latency, not CPU cycles. To my mind, their insights are pretty reasonable. They think, although both memory timing and CPU have both improved exponentially, the base of that exponent is much higher in CPU than it is in memory, and the difference between two exponentials is exponential. They reason based on the density of memory operations in your program, load and store instructions. If 20% of operations are memory accesses, then processor speed, counting cycles, counting operations, is a secondary consideration once memory takes 5x longer than a CPU cycle. They predicted that that timing barrier would be passed in roughly a decade, say 2004-ish, and that it might, oh no, grow to 100x by 2010. They were completely correct. What they don't say, but is highly relevant to this discussion, is big O is predicated on the idea that most operations are same-ish. And we focus so much attention on the worst case algorithmic complexity when what matters is, at least in data structures, average case and the effect of memory caching. And it turns out on average, hashes are substantially better algorithmic complexity, but average case analysis doesn't carry the same intellectual cachet and weight. So I think we kind of gloss over this point. And then there's this weird stuff about, well, it depends on hash function quality and how do you make up a good hash function? And that starts feeling insufficiently theoretical. And I agree, it kind of is. And honestly, leave that to the experts. But in related spaces, there is room for new theory and insights that I do want people to ruminate on, like associative containers are an important tool, and to incorporate ideas in how they build programs and represent data. Based on years of participation in the design for the C++ standard library, there's some things I've learned about how we represent objects in programs. For instance, hashing follows from equality. If you can define what it means to compare two objects for equality, hashing is always appropriate. It's an optimization of equality. It's fairly rare to have objects that don't logically compare to other instances of their type. And this, by itself, thinking about data representation and what works from a theoretical perspective, has a ton of downstream ramifications. It fits comfortably into plenty of programming languages and frameworks. Heck, this idea helps explain why Python is the way it is, because everything in Python is just the trick of, well, we can equality compare things, and hashing is effective. By comparison, once we get away from numerics, ordering is a relatively rare property for types. The example I always use is chairs. What's the natural sort order for chairs? Height, weight, color? What color space? Number of legs? Cost? If you want something more computey, how about JSON blobs? How do we sort those? Or objects that represent users. Do you really want to say this user is greater than that one? How often do we run through a container and need the results to come back out in sorted order? Turns out, almost never. Sorting is an interesting and important exercise, but a cost that we don't usually need based on operations that may not apply to the data that our engineers are going to spend all of their time dealing with. So reliance on operations that may be nonsensical, I would argue, is yet another mark against search trees. You can't just make up an ordering and hope that it's a correct canonical ordering for any given type, and not everything has a sensible comparison function to apply to it. Bring it back to memory latency and the criticality of cache misses. Modern high-quality hashes are a single contiguous allocation with the hash codes and table metadata stored as a prefix of the element storage, coupled with like SIMD parallel masking lookup to do multi-lookup of your hash codes in a single operation. Just a lot of fascinating stuff out there about this. Because like they said in the memory wallpaper, the goal is to make cache misses rare. Turns out a little bit of that is done by your compilers and language runtimes and all of the rest of that. But some of it, a lot of it, is manifested in our choice of data structures. And any data structure that isn't backed by contiguous storage is just awfully painful and slow. It's not fit for purpose in real world applications anymore. So we need to look not only at the average case, but also at memory access costs. The place for worst case big O analysis is not in how many loops you did, it's in how many memory operations are there going to be. Because at scale, nothing stays in on-processor cache, and the memory wall is going to dominate everything about the efficiency of our algorithms and programs. We have to remember that in modern software, an uncached memory access is comparable to the latency added by locking a mutex, uncontested mutex. Every random pointer traversal is pretty close to that expensive for a high-quality mutex. This means that every node you traverse in a linked list or a binary search tree is on par with doing a mutex operation. Even a balanced binary search tree is log n mutexes. Are you uncomfortable now? Please be uncomfortable. That is really expensive. Whereas for contiguous memory, because of cache effects and prefetching effects, you assume that memory access is free after the first hit, and in practice, you're pretty close to that assumption. In theory, there's no difference between theory and practice. The French did always covered binary search trees and linked lists and all of these things, but anyone that has to use a container in anger knows that big O is not the full story here. Not all operations are equal weight, and modern architectures have a weird tendency to make a bunch of things free and other things phenomenally expensive. So I'll just make the claim, with exactly 2 container data structures, you will handle the vast majority of your use cases. Specifically, you need a contiguous sequence container, an array, a vector, whatever that is in your language, and you want a hash-based associative container, which could be a set in the degenerate case, it's a map, a dictionary, whatever you call it. Those capture the absolute majority of the conceptual space, and teaching how to recognize which tool is appropriate and reach for those naturally is a critical skill for our students. We do still have to graduate students that have an understanding of how long an algorithm will take, and to do that is going to take some understanding of big O for sure. But if that isn't deeply tempered with nuance about memory and how computers work, then I think that we're doing them a substantial disservice. Moving past data structures, we could talk about recursion. During my tenure at Google, every single time I saw recursion used directly in the code, it was a bug. Without guaranteed tail recursion on any real-size data, recursion fails in most languages because of stack exhaustion. It tends to be slower, and it is unfit for real use cases. Going back to the phone screen example, every single time a student produced an answer that was recursive, it was in a language that didn't have guaranteed tail recursion, and I had already added inputs maybe up to 10,000 digits. Like, you don't have 10,000 stack frames, folks. Like, that's not how this works. It's an incredibly valuable concept that we do talk about regularly, and students absolutely have to have a conceptual understanding of it. But if you teach them recursion without teaching them when it's not a good tool, you're just encouraging them to run with scissors. Intelligence is knowing how to do something. Wisdom is knowing when not to. We need more of that. Knowing how to implement something recursively is lovely. Knowing when not to, because it's slower, more confusing, and less likely to work, is also important. Or regular expressions. In theory, regular expressions are a lovely way to apply ideas about finite state automata in a domain that people can relate to. In practice, it's a bucket of sharp edges. If you aren't careful in your choice of regex engines, untrusted inputs or untrusted regexes can lead to exponential explosion of memory or processing and a denial of service. Like, we actually have to worry about these things. And much like my point about memory operations being expensive, do you know how expensive it is to construct a regular expression? Like, code like this is deeply, deeply rotten because we're inside the loop, implicitly compiling a regex object to whole finite state automata every time that we go through the loop. And that is incredibly expensive. Code like this is less bad, but it might still hurt in a program that's hitting this function an awful lot of times. What we want is something like this. Right? We know the regular expression at compile time. It's silly to dynamically rebuild it over and over again. We should build it once. And increasingly, there are APIs in performance languages that do the finite state automata compilation at compile time, because there are cases where this matters. Tactically, my point with these examples is Students probably should have a conceptual understanding of search trees and linked lists and things like this because it is a useful structure once every few years. Or that recursion is a useful concept in conversation on a monthly basis, even if you shouldn't solve problems that way. Some linked lists and node, binary search tree assignments are probably a decent pedagogical exercise if you're trying to drive home the lesson of this is how pointers and object indirection work. But look at the research in this community, right? Students are substantially more motivated when you give them something grounded in reality rather than some funny applied math problem. There are other interesting trees and hierarchies. Have them implement and discuss family trees and think about the consequences of how they chose to lay out that data. There's some interesting discussions to be had there. If they choose to use a linked list without having unusual evidence about their access patterns, we have failed to give them an understanding of how computers work. If we keep doing that sort of thing, CS is going to be the math department, not the engineering department. Strategically, my point is bigger. An awful lot of what we teach in CS seems to me to be, this was a hot topic at some point in the last 30 years, or this is what was needed to implement a database or an operating system in the 90s. Some of those ideas have outlived their relevance, and we need to cull them real hard. Even more broadly, I will say, y'all are 100% correct. Don't swing your curricula based on the web framework du jour or whatever tech topic is trending. Like, please be slow when it's relevant to be slow. I'll be thrilled to discover that there's no classes endorsing Bitcoin. And I don't care at all whether students learn React or Angular or Vue or Svelte. But there are practical lessons of practical concern that do have lasting value. The fact that memory caches are a real thing, or multi-threaded code is an everyday concern. Industry professionals outnumber CS professors by about a factor of 100. And when we get it wrong, sometimes there are market-affecting consequences. So I implore you, especially those of you that have the flexibility to rewrite or burn down courses, take a good hard look at what you're teaching. Find your industry colleagues and friends and ask yourselves this for every single topic. Is it French dictionary? Are we teaching that concept for a real practical reason, or are we teaching it because it's tradition? We are far too young a field for tradition to be a major factor in these decisions. I suspect that there are people in this room that are older than the oldest CS departments. The AI storm is going to wreak absolute havoc on institutions that cannot break free of the shackles of, we've always done it this way, when we've always done it this way doesn't even go back that far. Right? It's not as set in stone as we make it out to be if we believe that it's fixable. So here's what is needed. Put absolutely everything under the microscope and be ruthless in cutting away the old ideas and concepts. We have evolved. We are being forced to evolve quickly, and it is time to break those chains all the way down to the level of what does an assignment look like? Because of scale and because of we've taken to meat grinder auto grader problems, and those are graded, like I said, on functional correctness and matching the spec. LEET code problems were also the norm for the interviews, so we were teaching to the test. But that is being thrown out the window because of AI as well. Producing the code on your own is not the in-demand skill. Knowing how to craft a thing of quality, of beauty indirectly, and to evaluate it for correctness, efficiency, security, whatever your quality attributes are, readability, maintainability, all of that, that is how we are going to hire going forward. Functionality is nice and is important and all, but AI can handle that. Quality is how we distinguish ourselves now. Assignments should be like art projects. Students are graded not on, did you implement this particular thing, but did you implement something? And then include in that evaluation their critique of others in terms of spotting bugs, inefficiencies, inelegant approaches, inconsistent style, confusing code. And the flip side of all of those, beautiful results, efficient algorithms, elegant approaches, like clear, clean, beautiful code. Grade their critiques on their ability to be polite and constructive and collaborative. Does it sound like grading hundreds of mini essays sounds terrible? Feed it to an AI, at least as a first pass. We can automate these things. If our colleagues in English departments can figure out how to grade papers, we can too. We've been taking refuge in the relative safety of functional correctness, of pretending that all of our discipline and all of our activities can be perfectly objective. And the result is that far too graduates have been instilled with any sense of the beauty or craft because the subjective things are now the only game in town. That is what they are going to be working with. We need to focus on grading process, not outputs, process, not product. The submission can no longer be just the code. It needs to be the code plus the prompts and the chat logs that got you there. It's the tests that you wrote to demonstrate to yourself that the code is correct before you submitted it. Give points for test cases that find bugs in other student submissions. Detract points for submissions that take longer on average to execute a malicious input. Subtract points for submissions that have redundant test cases. If they just throw everything at the wall and none of it is informative, that's not helpful. How do we possibly scale up to finding redundant test cases? You can look to industry. I've been talking myself for years about how to identify redundant tests in a test suite. It's a beautiful trick. It is off topic to fit in these slides. Ask about it afterwards or email me and I'll happily talk your ear off about it. We need to focus our testing on conceptual understanding. I do not need to know that you can calculate a checksum. I need to know that you understand when to use one. I don't need to see you prove type safety for a code snippet. I need to know that you understand what we're trading off when we lean on static or dynamic typing. At the curriculum level, if I had the power, this is what I would do. CS0 is for non-majors. It's not an on-ramp for CS1. And it could very well, and I think importantly, be just vibe coding 101. Let's democratize the absolute heck out of this, so long as people are made painfully aware that AI tools are going to produce risky code that is not necessarily fit for consumption by others. Society has a precedent for this. It is one thing for you to make a batch of cookies for your friends and family. If you are making cookies and selling them in my local grocery store, I would kind of like to know that your kitchen is going to pass health safety inspections. Same with software. AI vibe coding, even without knowing what the code really does, can be an incredible thing to give people more access to basic automation and the power to take control of their computing environment. But I don't want to be exposed to your slop or bad kitchen hygiene. There's a balance to be had here. For majors, I think we probably have to start without AI. You, I think, have to learn to read code first, but we'll need to figure this out. Some of this might also be learning to write, but to a vastly lesser extent than we currently focus. And the reading should not be, can you decouple or decipher these like 5 lines in a loop? It's, can you understand and synthesize larger meaning from a real corpus, like dozens of lines, hundreds of lines, functions, classes, what are we doing here? Within the first year, we need to move very quickly to scaffolded AI-assisted approaches. I don't think these are the general purpose LLMs. I think we need to, scaffold that carefully with a deep focus on how did you get here, not just what answer you produced. We need the students to be showing their work. It's exactly what math classes do to counteract calculators. Focus on evaluating the prompts and the code and the tests and the critique of other code. Figure out what it takes to teach poetry to instill a sense of taste and throw away all of the legacy cruft because it has no value anymore. As students progress through a program, make them take the time to practice. Give them the chance to broaden their scope. If you graduated music students with no required hours in the practice room, I suspect they're not going to be great at their instruments. We need time with scales and arpeggios to be good at the basic understanding of what we do. All right? Highlight the human parts of tech, right? Whether they're aiming for academia or industry, please, for the love of everything, focus on ethics and communication. Focus on how to design patterns, architecture, the difference between functional attributes and quality attributes. Do not worry so much about whether they've taken any given upper division topic, because one class on OSs or networks is not setting them up for a career in that field. It's giving them a very small taste of that. The amount of hours that you get from one of those classes is less than a month on the job, right? You're giving them a flavor, not expertise. They need more flavor and time on basics to gain expertise. Just like learning any skill, be it art or music, Focus time on practice and repetition and skill building because that's how we build taste. It cannot just be knowledge. Mastery comes as a function of time on task. I keep saying AI is making all of the old problems suddenly urgent. We've ignored for far too long the messy relationship between our current curriculum, CS theory, and tech practice. We've somehow gotten into the habit of focusing entirely on the theory as it existed a generation ago, as if those concepts and lessons are handed down on stone tablets. But in the AI age, this means that students are not learning relevant theory or useful practice, and that does not sound like a recipe for keeping our field relevant. Early in the talk, I mentioned I wanted to dedicate this to the PhD students and the junior faculty in the room. Hopefully you can see why. We're facing nothing short of a revolution. And it's going to be a lot easier for those of you without the institutional baggage to take up arms and burn down the crufty legacy that is not serving our students. Academic CS is at a crossroads. We can continue teaching linked lists and pretending that our lessons from the 90s are basically fine, or we can catch the updraft from the fires lit by AI and soar to new heights. We are the vanguard. Countless other disciplines are going to go through the same upheaval, but they do not have the same connections or insight into how to wrangle AI, nor do they have such an existential need to act soon. If we tear away the legacy that is not serving us well, if we go into this with eyes open and can take an honest look at how computers work today and what programming means in the modern era, we can be a lighthouse for other disciplines. We can show them the way to navigate this. We can guide them away from the rocks of AI slop and irrelevance. And it is largely a question of finding the will to shift approach, to try new things without full knowledge, without experimental results to prove that we're safe, to show the power of a focus on process, thinking, and quality, not just final results. That's been a concern with secondary education for ages. We all kind of know it needs to be done. The people in this room have the power to shape the next generation of technologists, to influence how education works across disciplines in the AI era, to think about what school even means. You have the power to determine that humans remain essential and relevant in our field. And the stakes are high because if we keep going down this path without radical change, boot camps and self-taught AI slop purveyors are going to dominate tech. Software quality will somehow get even worse, and some even more dystopian things seem pretty likely. It's all rocket-powered roller skates. The role of CS education is to pave that road ahead for the students, for our field, for the other fields that are facing similar disruptions. What got us here is not going to get us there. The stuff we've kind of known that we need to fix is urgent, more urgent than ever before. The power is yours for the taking. Please rise up. Thank you. Questions?
Hi there. Oh, do you want to go first? Or? Well, wow. No. I can see your hand. Did I win?
You win.
Okay.
You win.
Hi, everybody. Joe Porquet from UC Davis. Thank you so much for your talk. I'm very sympathetic to your French dictionary versus French poetry argument, not only because I'm French, but also like I think I'm the only one in my department. I worked a little bit in the industry and then I started teaching in academia. I think I was the only one in my department focusing on code quality and dedicating some TA time to that. And I did that for a few years. But I ran into like three very important problems, and I might like sort of redirect your argument back at you, which is like in theory and practice, there are no differences, but in practice, there are differences. The first issue is that TAs lack the experience to provide good feedback. That was step number one. we may argue that like, well, once we start teaching quality to students, then within a few years, TAs will be able to do that job, but right now they can't. Step number two, we have budget constraints in many institutions like mine. So now I have, for example, to teach like 200 students with two TAs.
Yeah.
I cannot grade quality anymore. And the third is that like for some reason, because we were teaching French dictionary, we thought, oh, teaching computer science can scale. And if we now want to say like, well, it has to be more like teaching writing, it doesn't scale. And actually, like my colleagues in the writing department, I talk to them and they still have classes of 25 students. And I'm like, okay, I understand you can do that. We can't.
Yeah.
And at the end, just to finish, like you mentioned, well, just feed it to the AI, but that kind of defines your point from the beginning, which is that like AI cannot catch, like AI is the one like producing the wrong, like the not optimized solution.
Yeah.
And we are supposed to have the expertise to get to the beautiful solution. So like, how do you reconcile all of that?
So for as much as I will poo-poo AI, it is a B minus version of basically everything. One of the things that's emerging in industry spaces is have AI agents that are specifically, I review code for security. I review code for efficiency. I review code for adherence to this style guide. And those are not perfect, but human review is not perfect either, right? Like one of the nice things about moving out of the binary world of functionality to the very gradient, like qualitative world of quality is you don't have to get everything. It doesn't have to be perfect. You catch as much of it as you can reasonably do, and you move on, right? So even like having some AI token budget and some tools to evaluate for quality should get you a substantial amount of the way there. I think the other thing that is really good is we need to incorporate the students' involvement in this as early and publicly as possible, right? Because you may have seen other talks from me, like I firmly believe that we are teaching all of our students that code is shame because they never actually see a professional or a fluent programmer programming, and they're told not to collaborate on code, and you only see like the only time their code is looked at by a human is to judge them. Like, oops, like, that's not the way to do this. Like, so in class, like, here was an interesting thing from an assignment. Like, student disagrees with grader or AI or prof, or two students disagree on, is this a good approach or a bad approach? Bring those up. Have a class discussion. Like, what are the positives and minuses? Do we know under which metrics we would prefer one versus the other, right? Those are important. Those are amazing lessons to get through. And so, like, yeah, it's going to be different, but even getting the grading done is part, like, can be a learning activity on its own. Does that reassure you at all?
Yeah, I'm still, I don't know how to scale that to like 100.
Nobody knows how to do any of this. Like, if there were answers, this would be easy. Like, yeah, like from an industry perspective, nobody knows how to do this either. Like, we're making it up as we go. Get comfortable being uncomfortable. Dan?
Hi, Dan Garcia, UC Berkeley. Thank you so much for A, an incendiary talk, B, a call to action, C, a talk that I think should require some more space to continue to talk about. I feel like you gave us like 5 minutes and there's like 20 people here to talk about really powerful things. So
I'm sorry.
No, thank you for what you said. Maybe a call on Audible and have a space where that can continue, maybe online on Hoover or something for the symposium chairs. I hosted a celebration of the award winners a year ago on a stage in Pittsburgh, and Mitch Resnick shared a perspective about AI that many of you might remember this great phrase, which was, I'm speaking to the comment of what CS0 should be. Do you want to teach young people? I'm connected to K-12. A lot of people in this room are K-12 connected. Do you want to have those students learn to play the stereo or learn to play the piano? And I think by saying, let's make CS0, which I think kind of sometimes reflects what you do in high school in some ways in upper high school, let's have that be about vibe coding. I think there is a population of students who want that. And I'm not going to say that's not a beautiful thing. I just need to get a working game of Tetris. I don't care about learning how to do it. I just want a working game of Tetris. And so there is a population, but it breaks my heart to think that that's what we should be doing for everybody, because the joy of being able to build it. Let's look at all the scratch kids of the world, right? Think about Mitch, who are now going to say, all we're going to offer you in CS0 and in that K-12 writ large is point at something and have somebody who's not perfect build it for you. Wow. Where's the next generation of painters and writers and creators? I have so much joy in programming. It breaks my heart to think that that's what we should be doing. And that's the message for the few folks who are doing CS0.
I think that there's room for both, for sure. Several people in the audience have heard me rant about this earlier. I'm sorry, I'm going to tell this one story and call it off the stage. I've been thinking about a lot of this in terms of fashion. Like, there's a great YouTube video I saw recently about the evolution of fashion from the 30s through the 50s. And automation, washing machines, factory processes, all of these things have led us to a world of like fast fashion, and garments are very different than it used to be. But there's a spectrum of quality, right? Like, you can go buy a t-shirt at the beach for $3. You can shop at Walmart, Old Navy, The Gap, Banana Republic, Brooks Brothers, made to measure tailor suit, right? Different levels of quality have different purpose. They're all valid, right? What we need to do is understand, like, are you in this because of the joy of sewing and craft and creation, or do you just need something to throw on and not get sunburned, right? And I think that there's a lot of access for, there's just this annoying problem in my life, but computers are magic and scary, that like, without giving them the depth, like, it's still improving their life and existence to be able to solve that problem for themselves. I desperately want more people to like then get curious and try to figure out what's under the hood. I think that'll be incredibly powerful. But we can't just get rid of, like, be entirely dismissive of the slop because a beach t-shirt is sometimes exactly the right souvenir. I think I'm being asked to be off stage. I would love to continue talking. I have to run to an airport before terribly long. Look me up online, or I'd be happy to do something later. I apologize that this is too fast.
Thank you. All right, thank you again, Dr. Winters, for your keynote. As we conclude our final plenary for TS 2026, we would like to thank again all of our in-person attendees, as well here in St. Louis, as well as those online on Zoom, for joining us here. We hope that the 2026 Technical Symposium will have a positive and lasting impact on your work and for your students. We thank all of our participants, volunteers, and service providers for their contributions and commitment to making the 2026 Technical Symposium a success. The exhibit hall is now open, so please visit with our exhibitors and enjoy some delicious snacks and coffee. And this concludes our closing plenary. Enjoy the rest of your 2026 Technical Symposium. Thank you.